rather than the zoom option to record. So you can tell that I'm recording if you see this little film right there, and it's red. Did you see that box that's all filled in shaded red there? That means that we are recording. So that's a way you can know that I am, because it's not going to show that we're recording on Zoom. All right, so I want to talk about, remember this we talked about last time in terms of how different applications use dot product and different use cross product, and the way you could know is by looking at your two vectors. If your two vectors kind of give you the maximum value of a quantity when those vectors are parallel or in the same direction, that's a matter of dot product. And when your quantity is maximized when your two vectors are orthogonal to one another, like we saw last time with the area of a parallelogram made by the two vectors, that's cross product. So what about with torque? So torque, first of all, torque is twisting force. So torque is twisting force. So how much? So you can imagine, turning a bolt. If you don't have enough twisting force on that bolt, it won't budge. And once you get to a certain amount of twisting force, then it starts to move. And with a high twisting force, it would move faster. You can imagine that. So torque is like twisting force. And there's two things involved. There's the distance from the center of rotation to the location where the force is being applied. That vector is called r. So it's kind of like radius, r for radius. So the vector from the center of rotation to where the force is being applied is r, and then the force itself is F. Okay, so then the question is, would the amount of twisting force be a matter of cross product or dot product of r and F? So we ask, is it maximized when these are orthogonal? Do we get the maximum twisting force when these vectors are orthogonal, or when they're parallel?
Orthogonal.
Yeah, so we can think about the components of F, right? So this is kind of at an angle to R. So here's the parallel component of F to R, and then here's the orthogonal component of F to R. Which of those components is going to cause the bolt to twist? And that would certainly be this one, right? This is the one, this is your best force to apply to get this thing to turn. This is just going to pull the wrench off the bolt. It's not going to contribute to any turning or twisting of the bolt. So, orthogonal, right? So the component of F that's orthogonal to R is what we're interested in to generate torque. Therefore, cross product. All right, and so the magnitude of the cross product is the amount of twisting force. Or turning force, if you either amount of twisting force. Okay, and so we know that the magnitude of the cross product is the product of the magnitudes in as much as they are orthogonal, and that's sine theta. So let's just confirm that. So when you do torque, you want to put that tail of the force at the tip of R, but then I move the force back here to see what the angle is. The angle theta, this angle theta, is the angle between the vectors tail to tail. So in this triangle, which angle is that? Is that this angle here? It's actually not, because this is theta. So in this triangle, this is theta. And that's why it's sine, because it's the opposite side. The magnitude of F, sine theta, gives you that component, that magnitude right there. That's what we want. So that checks out. So if you have theta, then you can calculate it this way. You can do the magnitude, the product of the magnitudes times sine theta. But this gives you another way to calculate it without having to know theta, and that is find the cross product. Do the algorithm I showed you last time, which you'll practice in web work, to get the actual components of R cross F, and then take the magnitude of that. So this way doesn't require knowing theta. But we saw last time they're equal, right? So the magnitude of the cross product is product of the magnitudes in as much as they are orthogonal, or product of the magnitudes times sine theta. Now, so this discussion is really about the magnitude of twisting force, but actually torque is a vector. It's not just an amount, not just a scalar. And so let's talk about the direction. What's the direction of the torque? Well, what kind of vector do you get when you do the cross product of two vectors? What's the direction of your resultant vector?
Orthogonal to the original two.
Right, right. So orthogonal to the plane of the first two vectors, or orthogonal to both of the first two vectors. So torque is actually going to have a direction that's in and out of your computer screen, or in and out of the page. And it's going to be by the right-hand rule. So put your index finger in the direction of R, because that's the first index, so that your third finger points in the direction of F. And if you do that, so
into the screen.
I'm getting out of the screen towards me. So you guys are looking at it this way. So I'm going to do R is going to be right, like mostly to the right and a little bit up. And then F is going to be like that, right? So do I have, can you see my fingers? Do I have R and F oriented correctly? R that way, index finger, F this way. So then by the right-hand rule, it's actually coming out of the screen, coming towards you. And so that means that in this case, the way that R and F are oriented, the torque is coming out at the screen. But what's cool about this is that if you were to actually turn, right? So this force is going to turn the wrench counterclockwise. When you turn counterclockwise, which way does the bolt go? Does it go in? Are you screwing it in? Or does it come out? You're screwing it out.
No.
Out. The top of the bolt is gonna come towards you, right? Because of the way it's threaded. Because of the way the bolt is threaded, when you turn counterclockwise, that bolt is gonna go towards you. And so that's the direction of the torque. So the way that bolts are threaded, it is in alignment with the right-hand rule. If you turn counterclockwise, the direction of the torque is out, the bolt comes out. If you turn clockwise, if you turn it to the right, then the bolt, it tightens, it goes in, and that's actually the direction of the torque into the page. So this, the right-hand rule is in agreement with how bolts are threaded that way. So that the bolt actually moves in the direction of the torque vector. So how bolts are threaded. Okay, so the magnitude of torque we talked about first, but then torque is actually a vector. It's truly the cross product of R cross F. So it has a magnitude, but also has a direction orthogonal to the plane of rotation, according to the right-hand rule. And that's in agreement with the way that bolts are threaded. If you turn counterclockwise, the torque is coming towards you, the bolt is coming out towards you. And if you turn clockwise, according to the right-hand rule, the torque is into the screen, and then that bolt actually moves in that direction into the screen. Okay, any questions on torque?
Yeah, Professor.
Yeah.
Um, so when you're saying that the way like bolts are threaded is in agreement with the right hand rule, does
Yeah.
that mean there's also a convention to like set up the cross product for like this kind of problem with like the lever arm first, or that like that R
Yeah.
it's like R cross F instead of F cross R?
Yeah, exactly. Yeah. So if it was F cross R, then the result would be in the opposite of the way bolts are threaded.
Okay, yeah, thank you.
Yeah, but torque is defined as R cross F, so you always just keep that order. Yeah.
Okay.
Yeah. Okay, other questions? Okay, we're going to move on to, so we're kind of done with dot product and cross product. You get your practice in the homework, get the support that you need. If you got questions, office hours and email instructor button, or you can just email me questions. So the next thing we're going to talk about is lines in space. Okay, so can you see this R3 with this point here?
Yes.
Yeah.
Awesome. All right, so just had that where I wanted it, and then okay, so lines in space. So the way that we define a line in space is we start with a point on the line. Okay, so here's my point on the line right here, and that is 3, negative 3, 2 for this example for developing it. So we start with a point on the line, and then we pick what's called a direction vector. So point. And direction vector. And then for this example, to get started, my direction vector is negative 1, 2, 1. So we got our point, 3, negative 3, 2. And the direction vector, negative 1, 2, 1. And so the direction vector is parallel or on the line. So the direction vector is like runs right on the line. Okay? So the first thing I'm going to do is I'm going to turn this point into a vector in standard position. And so then what are the components of that vector? What are the components of that vector then if it's in standard position and its tip is at 3, negative 3, 2?
The same as the point values?
Right. So that means that the vector then is the same as the coordinates of the point if it's in standard position. Okay, so I'm going to start with that. And then I'm going to take my direction vector and I'm going to put its tail at that point. So here it comes. Ready? There it is. There's my direction vector, negative 1, 2, 1. And I got its tail right there on the point. And so now you can imagine, can you imagine the line that we are building out of this point in this direction vector? So it would be this line in space. With our given point and our given direction vector, we're after getting an equation or a function that gives us all the points on this line. Okay, well now by putting the direction vector right there, I just found another point on the line. What's the new point on the line that I found?
Isn't it projection?
Plus B.
Is it the Z?
So so projection, it's not a projection. A little bit easier, than projection. What's that?
Add the vectors together.
Yeah, so do you see if I just add those vectors together, I end up with this point here. And if I think of them as a vector addition, I get this vector here. I get that vector. And so that vector is also in standard position, and it's telling me a new point on the line. All right, so there's my given point as a standard position vector, and then I took, what did I do? I took the -1, 2, 1. Yeah, so by adding them together, I get this new point. So the new point is, check my math, 2, -1, 3. Did I do the math right? Yeah, so now this red vector is the vector 2, -1, 3, pointing at that point, and that's a new point on the line. Okay, I want to generate another point. So would it be an easy way to get a third point?
Subtract the vector.
Okay, I could subtract. Let's see.
The vector again.
Yeah, so subtracting would be adding the opposite, and that would take me to a point down here. That's good. And then the other said add it again. So that's what I'm going to do. I'm going to do that one. Just add it again. So another -1, 2, 1 would give me, is it 1, 1, 4? So now this point would be 1, 1, 4. So by adding this vector 2 times, what did I really do? What's another way to think of that? Adding that.
Scale it.
Yeah, scaled it by how much?
2.
Yeah. So watch. So I'm going to take that vector, that direction vector, and I'm going to scale it by 2. And when I scaled it by 2, it's really like adding that vector twice, right?
So could you write an equation using like a scaled vector?
I think he's onto something.
Points?
So you want to do what? You want to start with the point that we started with, 3, -3, 2. And what do you want to add?
Plus some variable scale vector, or the same vector we were going off of -1 to 1.
Yep. Yeah. I mean, yeah, exactly right. So you were thinking exactly the right thing. So if I choose now any scaling of that direction vector, any scaling will get us a new point, right? Every scaling of that vector. So watch it here. I could scale it by 2.85, scale it by 4.5, scale it by -1.8. So I'm scaling the direction vector and then adding it to my original point as a standard position vector, and I always get a point on the line. Does it make sense?
Yes.
So to generate all the points on the line, then we want, like he said, we want a variable, we usually use t, a variable scaling amount of that direction vector. And when we do that, we get all the points on the line. So here's showing all the t values from -5 to 5. So t multiplied by the direction vector added to the original point as a vector can give all the points on the line.
So just make sure the red line has the same value as the direction vector, but is at the standard position.
No, the direction vector is the blue one.
Yes.
The blue. Yeah. So the blue vector is the scaled. It's all scalings of my direction vector.
Mhm.
The red vector then is what you get when you add the initial point plus some scaled version of the direction vector. And that red vector is actually like the answer. The red vector is all points on the line. You see that? Because
Okay, I see.
it's in standard position. So So this was what? This was our black. So the red vector is like all points on the line, x, y, z. Okay? Equals what? The black? That's the point, initial point as a vector in standard position, plus all scalar multiples of actually this whole thing is blue, which is all scalings, all scalar multiples of our direction vector v.
This be considered a parametric function.
Not this is actually a vector equation. It's not. Yes, it's about to be parametric, but in this form, it's not parametric yet. But they're like, I mean, they're like super close brother and sister. So yes, the fact that you recognize that is good, right? Okay, so you have all possible points. You have a given point, and then you have your direction vector, and you're going to scale that to any length, the way I'm showing here. And then by adding the black plus the scaled version of the direction vector, you get every point on the line, which is the red vector. So, could I have used, so this point, 114 is on our line. Could I have used 114?
Yeah. Yeah.
So is that the same or is it different? So is this the same or different than this equation that I wrote up here?
Different. I think it's the same because with a different value of t, you can get like the same answer, and t can be any number.
Okay. So is it different or the same? The answer is yes. The answer is yes. It's the same because in the end, they both generate the same set of points, all the points on the gold line, or all the red vectors. But it's different because it has the different mapping of t values to points on the line, right? So t equals 2 in this equation will give me a different point than t equals 2 here. So it's a different function, but they both generate the exact same set of points when all is said and done. Does that make sense? And so likewise, do I have to use -1, 2, 1 here? What else could that be? What's another possibility?
3, -3, 2.
3, -3, 2. So you added. Oh, that's the point. All right. So if you put 3, -3, 2 into here, then our line will be what? It will be parallel to this. Is that going to be the same line? Right? Because this is the direction of 3, -3, 2. So if that's your direction vector, then your line is going to be parallel to that.
Would we scale -1 to 1 to be any value?
That's right. So what we need is any vector that's parallel to this one. And that means so we could scale that to anything we want. So for instance, 10, -20, -10. So do you see that that's -10 times as much as that one? So that's going to be parallel to our blue vector, and this will also give me the same set of points when all is said and done, but it will have a different mapping of t's to the points. So it's different in that you have a different function of from t to your output points, but the same in that you get the same set of points when all t's are used. Okay, similarly, you could do use this point. 2, -1, 3 was another point on the line. And then, I don't know, negative square root of 2, 2 square root of 2, square root of 2.
So it's like it looks the same in 3 dimensions, but it's not in 4 dimensions. It's like a different object in 4 dimensions.
Maybe, yeah. Yeah, like if you're graphing like t is your input, one dimension, and then the remaining 3 dimensions is your output. Yeah, that's a way to think of it. Yeah, I think of it more like as a table of values, right? So if you were doing a table of values of t and x, y, z, the mapping will be different. If you choose a different point on the line or a different direction vector, then these pairs of t's and points will be different correspondence.
Okay.
But if you enter all real numbers for t, you'll get the same set of points from all of these, which are the gold line, right? All the points on the gold line.
Okay.
All right, so then, let's see here. So that's a big, okay, so that's a really big takeaway here. Given a line in space, there's an infinite number of ways to write that line because there are an infinite number of points you could choose and an infinite number of scalings of the direction vector that you could choose. Big takeaway. All right, so let's do the math. So then over here, so it's a general form of a line. So this is a vector. So line in space, all points x, y, z equals a given point plus all scalings of a direction vector. So this is the generic form for a line in space. It's called the vector equation. Okay, and so let's do the math on this. So if I did the math on this, I could add these two vectors together, right? So what would I have? I'd have so I would you just add x components, you add y components, and z components. That's how you add vectors, right? So my x component would be x naught plus t times a, then y naught plus t times b plus z naught plus t times c. And when you do that, you see that here's the x equals this, y equals this, and z equals this. So you get x equals x naught plus ta, y equals y naught plus tb, and z equals z naught plus tc. Okay, so what does that look like from calc? So the vectors are gone now, right? So we're parsing apart the x, y, and z coordinates separately, which are each a function of this variable t. Do you remember that from Calc 2?
There's the parametric.
Yeah, right. There's the parametric equations for the line. So these are, all we did was do a little bit of vector addition here, with scalar multiplication, vector addition, and it just, this thing falls apart into the parametric equations of the line. So again, so now here's your x naught, y naught, z naught. That's your given point. Your a, b, c is your direction vector. There's a vector parallel to or on the line. Okay, so going back to our line here. So is, I don't know, is 0, 8, 5 a point on that line? So the gold line that we wrote with this equation here, is 0, 8, 5 a point on that line?
No.
And how would you know?
So starting at 3, -3, how I thought of it was the first value of the vector is 0. So if we scale t, make t equal to 3, that will make our x point be equal to 0. And then we just do the same thing with y and z. 2 times 3 is 6. 6 minus 3 is 3. We don't get 8. It is therefore not on the line.
Good. So you can choose any of your coordinates, say x equals 0. If x equals 0, then we can figure out what the t would need to be to generate an x coordinate of 0. And so so you can do it by sight, but if not, you can just take the x equation in the parametric form, and you got so x equals 0. So 0 equals what? 3 plus t times -1. And so then t equals 3. So if this is a point on the line, then t equals 3 should generate y equals 8 and z equals 5. And what does t equal 3 generate? Y equals, so now plug t in for 3, you get -3 plus 6. You get 3, and t equals 3 makes 2 plus 3 is 5. Well, that one's good, right? So we got the right z coordinate for t equals 3, but we didn't get the right y coordinate. So 0, 8, 5 is not a point on the line, and I should have by asking the question that way, I should have put parentheses here, right? So if I'm asking if it's a point, then these should be parentheses. But what is a point on the line then?
0, 3, 5.
0, 3, 5, not 0, 8, 5, 0, 3, 5. That's a valid point on the line because all those coordinates you get from t equals 3. But 0, 8, 5 is not a point on the line because there's not one t value that gives you that ordered triple. So if your life depended on it and you needed to find a point on the line that nobody else in your class picked, what would you do to get a point on that line that you could be 100% sure that no one else in the class would pick the same point on the line? Give me a good t value that would ensure that.
1,357,759,651,321.
Yes. Yes, exactly. Or,
You do like 3/5.
well, 3/5. I would go with something more obscure, right? Like, so how about 3.928 pi squared, right? So
Yeah,
t could be
because
any real number, right? So t can be any real number. We're picking, nice, easy integers here to make the examples nice. But t can be any real number, any scaling of that. So if you wanted to guarantee that you got a unique point, just pick some crazy, value of t that no one else would pick. Yeah, I mean, just even the 3.928, right? 3.928 is even that's going to be pretty obscure.
I mean, it's like you can theoretically, count to infinity, but if you try the count, the spaces in between one number, if you can count to infinity going 1, 2, 3, 4, 5, but then there's the stuff like if you try the count from 1 to 2 using all the numbers in between, you just can't.
Exactly. Yeah, there's an infinite number of rational numbers, right? So thinking on the number line. So that this is just, you don't have to pay me for this. This is just free, but so there's an infinite number of rational numbers. A rational number is any number that's a fraction of two integers. So 11 over negative 37. That's a rational number. So so there's an infinite number of those, right? So there's an infinite number of those points. But
it's just crazy.
But if you were to come here and pick a number at random, like come here and swipe your finger on the number line, the chances, the probability that you get a rational number is 0. If you pick a number at random, you'll always get an irrational number. The probability of picking a rational number is 0, and the probability of picking an irrational number like pi or e is 100%. So that you can go meditate on that over the weekend. All right.
Is that because there can be any number, like because you can't physically measure the numbers after a certain point?
It has to do with cardinality. There are certain infinities that are bigger than others.
Oh, yeah.
So, yeah. So, if you want to talk about that in office hours, that's a fun conversation. Come visit me. All right. So let's look at this. What do we got? 4 minutes. Okay. So, find the equation of a line through these 2 points. Can you see this Word doc that I have up here now?
Yes.
So let's call this P and Q. So I want to write the equation of a line that goes through these 2 points. So whenever you're asked to find the equation of a line, what do you need?
You need a point and a direction vector.
You need a point and a direction vector.
So is the direction vector kind of acting like a slope in this scenario?
Well, slope is a single value that's a rate of change. So it's something. Yeah, I mean it's like slope to the extent that slope gives like the inclination of the line if you're drawing it. The slope indicates the inclination of the line, although it's not. You can mess with the scales and you can get different steepnesses for the same slope, but it's still giving you something, an indication of the inclination of the line, and so is the direction vector. But that's where the analogy stops.
Okay, I understand.
Yeah,
Thank you.
yeah. Okay, so to write the equation of a line, we need a point and we need a direction vector. So in this given information, do I have either of these? Do we have either 1 or 2? Certainly. I have P or Q. Take your pick, right? We said any point on the line will do. Okay, so done. I'll pick P. So 10, -8, 7. All right, and then what else do we need to write the equation of the line? A vector. So how am I going to get a direction vector or a vector parallel to this line? If points P and Q are on the line.
Find the direction vector between P and Q.
Yeah, find vector PQ, right? PQ, you should imagine that PQ is going to be parallel to that line. So what is PQ? It's going to be, we're going to do final mass initial, so I get -19, a 2, and 11. Check my math.
Yes.
All right, so, or I could have chosen the other point, right? Which is, this is another valid answer, -9, -618, plus t times. Now what's the realm of possibilities for this direction vector? Any scalar multiple of this. So I could do QP, which would just be -1 times this. So QP would be fine. Or 100 times PQ, pi times PQ. Any scalar multiple of this vector is valid to be the direction vector of the line we want. So just and again, reiterating the point that there's an infinite number of ways to write the equation of a line in space, because you can use any point and any parallel vector, any vector that's parallel.
So we can just always use any number, right?
No. You can't just use any number. You have to use a vector that's parallel to your line. The vector has to show the pointing in the direction of your line.
Oh, okay. Yeah, I meant for like t, like you said right now.
Oh, to generate, well, that's how you generate points. T is going to remain variable, right. And by changing t, so once you have picked your direction vector, you're not going to change it. Just you keep it, you pick it, and leave it. And then you start to get points on the line, you pick different values of t, and that generates points on the line.
Okay, thank you.
Yeah, but scaling this vector to get an alternate and multiplying by t are two different things. Does that make sense? There's the idea that we can scale this to anything we want, and it's a valid direction vector. That's one thing. And then once you have a direction vector, now you're gonna pick different values of t to generate points on your line.